Let's take a look at an example problem for Module 7.1. So in this example problem, example 6.1 from our text, they tell us that for an undamped single degree of freedom system from example 4.1, which we'll come back and reference in a minute here, they want us to determine the response for u of t from time from 0 to 0.2 seconds. In part A, they want us to do this by using the piecewise linear interpolation of the force with a delta t given to us as 0.02 seconds. Then in part B, they want us to evaluate the expression, the exact expression, u of t, at these same time steps. Now, if we go back to example 4.1 from chapter 4 in our text, this is a system shown down here in our figure 4.1 down here. It tells us our spring stiffness is K is equal to 40 pounds per inch. It tells us our mass weighs 38.6 pounds. Now, if the system is initially at rest, so there's another piece of information they give us, that is, our u of 0, or u at time 0, is equal to u dot of 0 is equal to 0. So if our position is at rest here, our velocity is going to be 0 as well. So when the excitation here, they tell us that p of t is equal to 10 times the cosine of 10t pounds, begins, determine an expression for the resulting motion, sketch the resulting motion. So basically we're going to reference back to this example 4.1 from chapter 4 in our text using this figure down here in order to answer this problem here, example 6.1. So now that we've had that opportunity to read through the problem statement, understand what they're asking, what they've given us between both of the problem statements and given diagrams, we can now create our setup page. So start here. The system shows we have a spring stiffness from 4.1 of K is equal to 40 pounds per inch and a weight here of 38.6 pounds. So again, here's all of our givens. Right over here, I have my K value, my weight value, and my P of T all right here, where this is my P naught in this expression for 10 times the cosine of my 10t here, and that is my omega right there. They tell us, again, our system is initially at rest, so we have this condition over here, u of 0 is equal to u dot of 0 is equal to 0, and our P of T is given to us by this expression here, which we showed up in our givens as well. Here's our given diagram right here. So we can see here's our mass M on a cart with wheels here, our P of T over here, external force there, our distance displacement U, and our spring constant right here, K. Again, we're determining an expression for the resulting motion in 4.1. So the first thing we want to do, now that we have the setup, is figure out what are our key equations. We know what they're asking for. We know what they've given us in the problem statement. What equations will help us get to that point? So for our key equations here, we have U is equal to u naught over 1 minus r squared times the cosine of omega t plus a1 cosine omega n plus a2 sine omega nt. Whoops, a t there as well. So this comes from equation 4.11 on page 84 of our textbook. So I referenced that down here. You can see I've boxed this in so we can reference back to our text, take a look at our general equation there. Now within this here, there are other variables that we need to know relationships for. So we have our omega sub n is equal to the square root of k over m. This comes from equation 3.4a in our text. Our u naught is equal to p naught over k, which comes from equation 4.4 in our text. And our r is equal to our omega over our omega sub n, which is equation 4.6 in our text, and u is equal to u naught over 1 minus r squared, which is equation 4.9 in our text. So these are all general equations, referencing back to where we can pull them from our textbook as well. So next, we can start our solution. So for part 1 of our solution, I'm going to use this equation 4.11 on page 84 of our textbook, where we have that u is equal to our capital U naught over 1 minus r squared times the cosine omega t plus a1 times the cosine omega nt plus a2 times the sine omega nt. To get the velocity, we can differentiate this equation right there, and when we take the first time derivative of this equation, we end up with a u dot, and we get this expression here. Our negative capital U naught omega over 1 minus r squared times the sine of omega t minus a1 omega n sine omega nt plus a2 omega n cosine omega nt when we take the derivative. So then we can, from here, solve this expression for our omega sub n using this equation here, which is 3.4a from our text. So I'll redraw that out here right from our textbook there. Omega n squared is equal to k over m. So now we'll begin our solution for omega n from that equation 3.4a. So omega sub n is equal to the square root of k over m. Well, we're given a weight, not a mass, so we can take the square root of k over weight divided by gravity here to get our mass term there. We can rearrange this slightly, and this becomes the square root of k times g when we put the g back up top here, divided by m. So recall weight is equal to mass times acceleration due to gravity, so mass is equal to weight over gravity. That's why we're able to plug this in right here. So what is our gravity term? Well, 32.17 feet per second squared. But if we want to be in units of inches per second squared here, our gravity is 386 inches per second squared. So we can plug that in now to this equation here. So omega sub n is equal to the square root of our k value of 40 times our g of 386 inches per second squared, all divided by our mass here of 38.6. So then from there, we get now a value of 20 radians per second is equal to our omega sub n. So now we have a value for omega sub n. From there, we can solve for our static displacement, and this comes from equation 4.4. So our u naught, capital U naught, is equal to P naught over K. Plug in our value here. Well, we can solve for this here. We have a 10 pounds here divided by our 40. So therefore, we have our U naught is equal to 0.25 inches. We can then use equation 4.6 to solve for our R value. Right there, where R is equal to omega over omega sub n, which is 10 radians per second over 20 radians per second. We plug in our known values. So our R is equal to 0.5. So now we'll solve for our U value here from equation 4.9. We have that our capital U naught is equal to 1 minus our R squared there. So we've already solved for our U naught over here as 0.25 inches in the previous slide. And we have 1 minus our R value that we solved for of 0.5, so we can plug that in here. We end up with is 0.25 over 0.75, or 1/3 inch. So we have this relationship down here where capital U is equal to 1/3 inch. So now we can jump to equation 4.11, and we can use our initial conditions with this in order to solve for our A1 and our A2. So we can see there's an A1 and an A2 in this general equation here. So we've already solved for this in the above expression from 4.9 right there. So we can plug in here our U value down here for this relationship here. And then we have times the cosine of omega t plus our A1 that we're going to be looking for times the cosine of omega nt plus our A2 that we're looking for times the sine of omega nt here. Start plugging in our known values, so we can plug in that first part of the equation here, becomes our 1/3 times the cosine of 10 times 0, because we're doing it for our initial conditions there, plus A1 times the cosine of our 20 when we plug in here, times 0 for time, plus A2 times the sine of 20 plus 0 for time. Certain ones of these, our cosines of 0 are going to go to a 1 right there. Our sine of 0 goes to 0 there. Cosine of 0 goes to 1 right there. This greatly reduces and simplifies down, so we end up with U naught is equal to 0 is equal to 1/3 plus our A1, or A1 is equal to a negative 1/3. So we're able to solve directly for our A1 we wanted to do up here using our initial conditions and known values. So in order to solve for A2, what we're going to do is we're going to take that derivative of that expression from 4.11, where we have our U dot here is equal to our negative U naught times omega over 1 minus R squared times the sine of omega t minus A1 omega n sine omega nt plus A2 omega n cosine omega nt. Plug in our known values. This is for our initial condition, so our at time is equal to 0. So our sine, this will go here of 0, sine of 0, and we have our cosine of 0 over there. So some of those terms drop out, some will go to 0 there. What we end up with now for this expression here is omega dot of 0 is equal to 0 plus our A2, because our A2 is the only one here that's going to have an expression right there, because that goes to a 1 there, times 20 radians per second times the cosine of 0 right there. We can plug in there, so our U dot of 0, our initial condition of 0, is equal to our A2 times 20, divide both sides by 20. We end up with this relationship here, or A2 is equal to 0 when we solve it for A2. Next, we're going to use our total response equation here. So we have our U of t is equal to, now the same expression that we've seen before there that we already have a value for, our U naught over 1 minus R squared, times the cosine of our omega t, plus A1 cosine omega nt, plus A2 sine omega nt. So back into this general expression here, plug in our known values. Well, we already solved this to be 1/3. Plug in this here, we know our omega is 10. We now have an expression for A1, which is negative 1/3. We now have an expression for A2, which is 0. So we can plug this all in here. So if this is 0, this whole term is now going to go to 0 there. So we can reduce and simplify. U of t is equal to 1/3 times the cosine of 10t minus the cosine of 20t, and this gives us our answer for our U of t. So now that we have our U of t expression, we can move on to what they're asking us to solve for in our example problem 6.1. So in 6.1, they want us to determine the response for this U of t that we just solved for time from 0 to 0.2 seconds. They want us to do this by using the piecewise linear interpolation of the force with delta t is equal to 0.02 seconds for part A. And in part B, they want us to evaluate the exact expression for U of t at these same time steps. So we know from our previous example 4.1 that our K is equal to 40 pounds per inch, omega sub n is equal to 20 radians per second, and our P of t is equal to 10 times the cosine of 10t in units of pounds. So as we start this here, first thing we want to do is take a look at what they've given us, what they're asking us to solve for, and come up with what our key equations are. So in this case here, our key equation comes from equation 6.7 on page 150 of our textbook. And on 150 of our textbook, we have this u sub I plus 1 is equal to a sub pi plus our b sub pi plus 1 plus cui plus dui there. And we have the derivative of that as well in this expression here. So we have this equation is given to us as our general equations we're going to use from equation 6.7 on page 150 of our text, where these coefficients can be obtained by setting our beta is equal to 0 and our omega sub d is equal to omega sub n, and then looking at table 6.1 in our textbook there. So here is equation 6.7 directly from our textbook down here. So now we'll take a look at this table 6.1 here. So this gives us the coefficient of reoccurrence formulas for underdamped single degree of freedom systems right here. So we can see we have A through D, A prime through D prime right here, and the associated relations and expressions with each of those. Again, for us, we're going to say our beta is equal to 0, omega sub d is equal to omega sub n, and we're going to say our delta t is equal to an h value right here. So we can go through and simplify this down for our particular case here. So off to the left, I have my value for A, B, C, D, and A prime, B prime, C prime, and D prime over here. So I can start reducing and simplifying these equations. So my A simplifies down to this expression here. So on and so forth. B simplifies down, C. So we can see we can get an expression for each of these coefficients here, where if we plug in our known values, our omega n times h is really 20 times 0.2 or 4 radians. Our sine of omega n h is equal to the sine of 0.4 radians, or our value here of 0.38942, and our cosine of omega n h is equal to the cosine of 0.4 radians, or 0.9106. So we can now even simplify these down a little bit further as well when we plug in our known values. So we plug our known values into each of these expressions here. We can see now our A, when we plug it in, now becomes 1.3.12 times 10 to the negative third. Our B, when we plug in our known values, becomes 6.613 times 10 to the negative fourth. C becomes 9.211 times 10 to the negative first. D becomes 1.947 times 10 to the negative second. Our A prime becomes 9.604 times 10 to the negative second. Our B prime becomes 9.868 times 10 to the negative second. Our C becomes negative 7.788, and our D becomes 9.211 times 10 to the negative first right there. And I've rewritten down our general expressions over here for each of those before we plugged in our known values, so you can see exactly how we plugged in for each of those expressions from the information and simplifications from our table 6.1. So now we want to see how does this compare based on our numeric solution based on linear approximation of the excitation to our exact solutions. We want to compare those two here. So we can go to this table 1, go to our u sub I, which I've circled in red here, and we can take a look at those versus our exact expressions here. And from our exact expressions, we can plug in our values for our I from 0 to 10, for our t sub I here from 0 to a 0.2 over here, going in steps of 0.2 as I move up there. So I can plug those into this equation here. Now you can do this in MATLAB, you could do this in Excel, you could do this by hand, you can do it with your calculator, Python, whatever your preference is. Then we come up with these numeric values here, which we can then, for these time steps here, same as our i's over here and our times right here, those are the same. For that and that, we can compare these two values from our exact solution to our piecewise linear interpolation up here. And if we want to calculate the period for the excitation, period is 2 pi over our omega there, or our period is equal to 0.628 seconds.